Good afternoon, Dr. Jangir.
Good afternoon, Altaf. How are you?
You're not audible. Not audible.
Oh, you can't hear me?
Yeah, okay, sorry.
Yeah, I can hear you.
No, I was connected through earphone, so I couldn't
Okay.
hear you properly. I didn't. I have conducted 5 sessions. One was conducted by Professor Saidulu on Saturday, and
Okay,
then
okay.
it was followed by two by me. And yesterday we had again 2 sessions for the tutorial.
Okay, okay.
So
How
now
did
one tutorial is
how did it go, the tutorial session? Because I'm also thinking to run one or two.
yeah, that is for the participants to tell. Anyways, one more is pending, as I said. So that will be taken on Friday after your session.
So your tutorial was problem solving or uh,
Yeah, on
like
Sunday I had a problem solving. What I did was I had my publication. We tried to implement that part. A part of
okay,
it.
okay. So it's more like publication related, research related.
Yes, yes.
Okay.
A small calculation based on battery charging, discharging, pattern for battery charging and discharging.
Okay. So how many will go for exam? Like
I think so.
all is
I think so. There were three till now.
free.
As per the
Okay.
information that I have collected recently, we'll just wait for a day, I think so.
Okay.
But I have actually shared a form with them to be filled. So once I get the data from there, I'll be able to exactly tell you as to how many have opted for grading also. I think so. We'll start in a minute or so because the participants will keep joining. We have 20 already.
Yeah, I think 20 is good enough to start.
Yeah, we can. It appears to be Monday blues today.
Yeah.
Maybe.
Um,
I have sent a message. Let's see. They'll join in sometime. So we can start, I believe.
so Altaf, can you confirm me? You can see my slide and I'm audible.
Yes, yes, confirm both the things.
Thank you. Good afternoon, everyone, and welcome in the second week. So that's the day 6 for us. So today I'm going to talk about wind energy. But before starting wind energy, few minutes, I'll just talk about briefly about renewable energy, and then I'll go details about wind turbine. But before starting, can I ask anyone from attendees working on wind turbine? Or anyone is planning to work on wind turbine? Okay, if not, then I'll continue. So as I said, like before going details about wind turbine, just few minutes I'll talk about different renewable energy sources. So as you know that so far still fossil fuel are a dominating source of electrical energy, and mainly there are three different source of fossil fuel, that is coal, oil, and natural gas. Still major portion of the energy both in Australia as well as India are producing these three different sources. And you know that issue with the fossil fuel sources, that they are not environment friendly, they are not sustainable. That's why, I mean, in recent year, government and industry now they are looking to get alternative source of power. So as I mentioned, like that's the majority power is producing from these three sources. And here also you can see like from this diagram that oil, gas, and coal, those are three are major, and then renewable hydro, nuclear. I mean, renewable hydro is also like one type of renewables, but hydro is not new. They have been utilizing this source for like so many years. So that's why when I say like renewables, people always think about mostly like the new technology like wind, solar, biomass, and so on. And this one again, I'm showing the same thing that even like by 2030, although I mean the renewable generation amount will increase, but still I think there will be coal, gas in most countries. But in coming years, by 2050, as we know, that's most country now they have promised that they will go carbon neutral by 2050. And to do that, we need a generation mix, not only the fossil fuel, but the majority generation, as we say, like it will come from renewables. Other could be that there could be some storage, and even if there is some like natural gas might be in the system, but they will be using carbon capture and storage. So that's how probably they will be going carbon neutral. So here it just shows like some estimation that by 2050, that's renewable would be almost 90%, and out of them variable would be 63%, and as I said, the remaining 10% might be coming from gas. But to decarbonize that, it will be it will use carbon capture and storage technology. So you might know that this technology also using in different country, including Australia as well. As I mentioned that although wind and solar are main source of renewable energy, and I also mentioned that hydro is in the power market for a long time. But other than that, there are also like biomass, tidal, geothermal, and other sources say like that hydrogen. And tomorrow we'll be talking about hydrogen in details. So I already mentioned that these are the main sources of renewable energy. So far we have already talked about solar. Hydro is not a new technology, so most of the electrical engineer, they already have some knowledge about hydro, so we are not repeating that one. I might give a brief discussion on biomass later in this week. We also have geothermal, but so far in Australia, geothermal is not popular because most of the places where electricity can be generated from geothermal that are far away from the load center. So sometimes just like to transfer that power from that particular location to a grid, we need a sometime like a like 1,000 kilometer long transmission line. That's on like there are a number of projects have been completed, and they found that at the end, the power that they will produce and the long transmission line they have to build at the end, I mean, it's not economically feasible. But in other country, it might be feasible. So that's the total energy statistics in Australia. So it's just for the 2019 to 20, there are just some comparison that's due to improvement in the energy efficiency. Energy consumption has gone down by 3%. Residual energy consumption has increased a little bit, but the commercial have gone down. Natural gas almost 40%, mainly used in the manufacturing sector. 54% electricity generation from coal in 2020. There was a massive increase from solar. It was like 42% increase. Transport sector, their energy consumption has gone down by 9%. Natural gas consumption have grown by 8%. So this is just some statistics for last years. So by 2050, by 2020, Australian government did have a target to produce at least 20%, and they have actually made that target. So now I think we have got more than 20%, like 23% generation is coming from renewable. Now the next target for Australian government by 2030 to have at least close to 70% from renewables. And you know that some country like Norway, they have got close to like 90% energy coming from renewable. And out of that, actually, a major portion is coming from hydro. But they have also like massive wind turbine as well. This one, just like that energy capacity that's coming from wind. And you can see like from 2011, like it's increasing every year, but last 2 years actually it has increased significantly. And there are a number of wind turbine projects are already going on. So if that project is completed, even like in the next 2 years, they will also have, significant growth in wind sector. Now, if you think about like different technology that's are being integrated to the current grid, and probably you have already heard something from Altab and other lecturers. So they have probably have given some like discussion on renewable energy challenges. Now here, if you think about the total grid, there are some of the concerns that the current power grid have. One of them is that in recent year we have got limited expansion of transmission network. If you think about the integration of new generation technology, so there are, as I say, like number of small scale distributed generator have been integrated in the grid, but there has not been that much expansion in the transmission network. Also, like most of the generation, transmission and distribution system have become old. Many of the system in Australia now almost like 100 years old. And due to that, the losses in the transmission and distribution system have gone up. So still for the although for the transmission system in Australia there are good visibility, but still for distribution system we have got lack of data for monitoring and control. There are increased concern regarding the vulnerability and resiliency of the system with distributed energy resources. And as you know, that's mainly happen when there are internal or external disturbance that can happen in the system. In recent year, you also know that there is a growing environmental concern. That's why most countries have set the target to become carbon neutral by 2050. Due to integration of different power electronics fed distributed generation, there is a huge problem in the power quality as well. The other issue is also like the energy management, and also the demand and load flexibility. That also issue for the current as well as the upcoming grid. Now, what is happening in recent year in the power grid? There are different types of new materials has been utilized. For example, polymeric, composite, nano. Even people are thinking about the superconducting materials as well for machine and even for cable as well. As you know, that superconducting material, their efficiency is very, very high, but there are some issue to maintaining the temperature for that materials. Also, in recent years, size of insulator is getting lower. Size of machine is also getting lower due to increased efficiency and also higher power density. Rating on machine is increased. There are different sources of alternative and renewable energy sources, as I already mentioned. That's coming into the power grid. There are a number of new devices and technology also coming in the system. For example, new power electronic devices, that is smart converter, fax devices, power quality controller, that being integrated in transmission and distribution system. There are also like DSP sensor, smart meters. They are also coming in the system just to improve the visibility and also implement wide area control. The system is getting more intelligent using AI and machine learning techniques. And there are also like increased use of information and communication technology. For example, IoT, machine learning, blockchain. So due to that, the system, as I said, getting more and more intelligent and also controllable as well. So that's how it's making the system more reliable, flexible, and resilient. Other things that's also coming in the system, that's wide area monitoring system, that I already mentioned. SCADA is already there, but also coming even like the better SCADA in the system. Also in coming years, there will be some power quality monitoring system as well. That would be mainly in the microgrid and smart grid system. There will be also like regulatory changes in the electricity market as well. And the reason is that the customer, as you know, that's their being like a prosumer, not only consumer, because they're also generating electricity. But in the coming years, they'll also be, participating in the electricity market. So that's why there are many new policy and regulation standard, that will be coming in the, electricity power grid. So as I mentioned, there are number of challenges as well as opportunity as well. Now, what do we need actually for this upcoming grid? So we need a wide area monitoring system just for online monitoring, so that you exactly know what is happening in which part of the system. And also we need intelligent control, which can act based on the changes that can happen in the system. We need a more secure, reliable, and green power supply, and that will mainly come from renewable energy sources as well as microgrid and smart grid. We need a system where customer will be dominating the changes that needs to be done in the system. So far in most country, customer is given very less priority. They are almost like a passive part. They just use electricity and they just pay the electricity. That's all. Other than that, they don't have any direct engagement and interaction with the power utility. But whatever concept that we are talking about now, like either microgrid, smart grid, demand side management, nothing is possible without active participation of the customer. So that's why, in many countries, even in Australia, now the power industry, they are trying in different way just to, improve their relation with the consumer, and also like restore the trust with the customer, because not only in Australia, but even if you do survey in India or other country, in most of the cases, you found that in most of the cases they don't have any trust on the electricity provider. And there are many reasons to that. If you compare, like for example, other sector, for example, like let's say like the banking sector. So if you think about the banking sector like 10 years back and the way that they are operating now, there have been a massive change in the banking sector. Now, in most of the cases, whatever you want to do in the banking sector, you don't have to go to the branch. You can do everything from your home. So their system, have achieved a massive improvement if you compare with the power grid. But that's a good news that um, power industry have realized that, and they have already taken many initiatives to improve their relation with the consumer. Other than that, we also need like the coordination among all the devices in the system, because if we just operate like either different parts of the system or different devices in the system locally, in the coming years it would be very difficult to maintain the reliability and also like get the flexibility that we need for the future grid. So that's why in coming years we need more like coordinated operation. Also, it makes sense to have more distributed generation close to the load center where we are actually utilizing the energy. And also we need harmonized legal framework. So whatever standard regulation we use, that should be standard for like all over the country. For example, if we talk about in Australia, we have got 6 state, 2 territory, and every state, every territory, they have got their own regulation, and sometimes their own standard, and that's how sometimes it makes more difficult, to have that coordinated operation. So probably that's why we also need a more standardized legal framework for the whole country. So that's all. Like more about like renewable generation as well as the power grid. Now I'm moving to wind turbine, because that wind turbine is one of the dominating source for renewable energy sources. And the reason it's getting popular, there are a number of reasons. As you know, that this is clean. There are no emissions that's coming from these sources. It does not have that much negative impact on water quality, although there are probably slide on the air quality. And also it does not have any negative impact on the climate change. It also help to reduce the fossil fuel dependence. It also improve security for national domestic energy supply, so you don't have to depend on other country to import coal, gas, which we are currently using, and this is renewable, and the source is free of cost. And also if you compare with the photovoltaic system, it needs less space to produce the same amount of power. Now it's actually not new that currently we are utilizing wind energy. We have been utilizing wind energy for many years. Previously, you might know that we use that windmill to produce useful source of energy from wind. But we normally did not use that one to produce electricity. We use for wind pump for water pumping or drainage, or sail to propel ships. So that was the uses. If you think about the mechanical energy that previously we used to use, but in recent year, that we are utilizing that wind energy to produce electricity using wind turbine. And if you think about the the overall system, it's more like same as photovoltaic system. So for the photovoltaic system, we use sunlight, which use as input for the photovoltaic panel, and then we use power converter inverter just to control that energy and convert it, which can be directly used to a load or can be transferred to the grid. So the wind generation system is also quite similar. Here also we use power converter like the photovoltaic system, but here we are using the kinetic energy available in the wind as input, and here we have got a turbine and generator, like a coupled system. So the turbine produces mechanical energy, mainly the rotating mechanical energy from that kinetic energy which is available in the wind energy, and then we convert that mechanical energy to electrical energy by using generator. And we use different types of generator. We'll be talking about that in details in later slide. But so far, I mean, is there any question or comments?
Any questions?
Any question or comments about either grid challenges, different source of renewable, or wind turbine?
I don't think there is a question.
Hope, I mean, because this is very basic concept, hope everybody understand that. So I already mentioned like what are the advantages, but there are some problems as well. As you know that the energy that we are getting from the wind turbine is not steady, is variable, and also I mean it's not a dependable source, because the power that we are getting from wind, it depends on the input energy. So this is like a non-displaceable source of energy. Depending on the size of the wind turbine, we classify it into three categories. It's called like small, medium, and large. So when the energy rating for a wind turbine like a 0.5 to 10 kilowatt, we call it a small wind turbine. So that's you might have a like a in a like a single premises or sometime in the residential site, and we use like a small vertical wind turbine. Medium one, 10 to 100 kilowatt. If you need like for a community, then you can have like a medium wind turbine. And if anything more than like kilowatt or 1.5 kilowatt, we call this is like a large wind turbine. But again, I mean, this is not hard and fast rule. So this is just like a range where you can classify into these categories. So this is just like one of the recent wind turbine. And this is the company who is like having this wind turbine. This is like one of the high capacity wind turbine. You can see it has got more than 8 megawatt capacity. The rotor diameter is 164 meter, and also the height is 220 meter. So if you need like want more or higher output power, your diameter and also the height, will be higher as well. And there are some relation, mathematical relation between capacity, diameter, and so on, and we'll show you those equation in coming slide. These are the just like history of wind turbine in terms of its sizes. So you can see that in the 90s, we have got wind turbine which is like less than, it's like a half a megawatt. And it was like 40 meter rotor diameter, and then the capacity have gone up in recent year. And as I mentioned already, we have got in the range of like a 10 megawatt wind turbine. But who knows, in coming years, we might have like 20, even like 40 megawatt. But still, this is not certain. This is just something like a guess. So that might come in future years. So there are number of parts in a wind turbine. So here I'm just showing few main components of a wind turbine. So here you can see that we have got nacelle, tower, foundation system, control system, transformer, and electrical connection. So in most of the cases, we got the transformer here. And then like this is we actually call nacelle, which have got both the generator as well as all the inverter control system. And this is like, there's the blade, and that's the tower. And we also have all the control system in the nacelle as well. So I already mentioned this, the different parts of that wind turbine, and each part have got their own function. So the main function of the blades, just to capture the kinetic energy that's available in the input wind. So the blade actually they rotate comparatively like a slower, lower speed, but the generator have got a comparatively higher speed, and in between there is like a speed conversion, and I'll be talking about that in incoming slide. And the nacelle, as I already mentioned, which is actually called gearbox, you already know about that. The nacelle, as I mentioned, like it has got here like the generator as well as gearbox, and this is tower. I already mentioned this. It depends on the capacity of the wind turbine. So if you have got higher capacity, the height of the tire will be also higher. But although I have mentioned only the few like components of wind turbine, but if you think about the individual parts, it actually read more than 8,000 parts in a single wind turbine. So there are so many individual part in a wind turbine. And like in a solar photovoltaic system, again, if you would like to analyze the wind turbine performance, we need to know the mathematical model. And here, as I mentioned, in the input side, the blade, which actually capture the kinetic energy, and then it's convert to the mechanical energy. And these are the well-known equation for the kinetic energy that's we use to calculate the kinetic energy, and that's also depends on the two factors. You probably already know about that. It depends on the mass as well as the velocity. So once you know the mass and velocity, you can easily calculate the kinetic energy. And from this, actually, similar equation, if you just represent the mass like in terms of area and density, because that's it has got relation with density, area, then you can just represent that the same equation using this equation. This is like a constant. This is like that, velocity, and this is like the area. So using this one, you can easily find out, like for a particular wind turbine, what's the input energy that's coming for a wind turbine. And this is just like one example. The rho is like the specific density for air, and this value is 1.23 kg per meter cube. Now here you have got a wind turbine with a speed of 20 meter per second, and it has got a blade length of 30 meter. So with that one, if you just utilize that equation, calculating that area, you can easily find out what could be that input power coming into the wind turbine. This is not the output power, but this is the wind input power. And so for that particular condition, so the input power is coming like 13.91 megawatt. This is very simple equation. And as you can see that the relation between the power and the diameter or radius, it has got the relation of like, when you're calculating, it has got relation like square. So in case, if you have your um, radius or diameter double, your power will increase 4 times because the relation is squared, as I mentioned. So if you double the rotor diameter, this means that your power will be like 4 times. And this is just giving like some of the standard diameter for different wind turbine with those power rating. But that's the input power. If you would like to calculate the output power of the turbine, the power that you're getting output from the turbine, you need to multiply that what could be the efficiency of the turbine. Because as you know, the relation between output and input power is given by the efficiency. Efficiency is the ratio of output and input power. So the equation that I have shown previously, if you just multiply like a power coefficient, which is also like efficiency in this case, you'll get the output power. Where Cp here, we called it power coefficient. And in most of the cases for the wind turbine, so the maximum value that so far has been achieved, its value is given like around 59%. So far, as I say, like the design that we have come up with the turbine, so the maximum efficiency we can get it 59.3%. So in case like you have got 100 kilowatt power available in the wind energy, for the turbine, you can get 59 kilowatt as output for the wind turbine. But again, that's not the final output of the wind turbine generation system, because after the turbine, you also have a generator, and then you have got inverter converter. And the relation with the wind speed, as you see the power, the relation is like a cube. So if your wind speed like becomes double, your power will increase by 8 times. Here it's just given like 2 example that if your wind speed like 8 meter per second, you are getting like 314 watt per square meter. But if your wind speed is double, you can see you are getting 2500 watt per square meter. So that's why the wind speed is very, very important. While you are designing a wind generation system. So the area that you would like to install, you have to make sure that you have got like sufficient wind flow for most of the time of a day. Now, as I mentioned, that there is a relation between blade diameter and output power, and that's the equation that I already mentioned in the previous slide. Where this is the velocity, this is the area, this is the power coefficient, and this is the air density. And here, this is the relation probably all of you know between the diameter and area. And if you just use some, for a particular wind turbine, let's say like a 10 megawatt wind turbine here, our blade diameter is like a 152 meter. And here, if you just simplify this equation, we can just make assumption like this one. This one will not give 100% accurate parameter, but you will get very close relation between the diameter and output power. So initially, just for the assumption or the rough calculation, if you want to like to make like that for a particular wind turbine power, what would be that diameter. And here this is just for a wind turbine in the Norway, 10 megawatt wind turbine. So the original diameter is 152, but from that calculation you are getting like 144 meter. So although there is a difference, but as I say, it will give you the rough calculation. There are some terminology you need to know if you would like to study wind turbine, and there are 4 different speed or wind terminology that we utilize when we design or analyze wind turbine. The first one we called it start up speed. So this is the minimum wind speed at which the rotor and blade they just start to rotate, but you are not getting any usable power from that. So the next one we call it cut-in speed. Cut-in speed is the minimum speed, wind speed, at which the wind turbine will generate usable power. And this is mainly like 7 to 10 mile per hour, but in terms of meter per second, this is equivalent to 3 to 4 meter per second. So if your wind speed like this rate, wind turbine will just start to rotate and get like a minimum usable power. Then the next terminology is called rated speed, and this is the minimum speed at which the wind turbine will generate its rated power. For example, if you say like 10 kilowatt wind turbine, which will not generate 10 kilowatt until your wind turbine reaches like rated speed, which most of the cases 12 to 17 meter per second. And in mile per hour, it will be like 25 to 35 mile per hour. And the last one, we called it cut-out speed. And this is like, very high wind speed. Typically more than like, 25 meter per second or 45 to 80 mile per hour. And this is the speed at which actually we completely shut down the wind turbine for the safety reason. For example, let's say if you have a wind gust or tornado, then for mechanical safety, there is some sensor which sense that speed and then it shut down that wind turbine. So if it goes in most of the cases more than 25 meter per second, the wind turbine will be shut down for the safety reason. And this is the safe thing. It's just shown graphically that this is the cut-in speed, like 3 to 4 meter per second. And when the speed goes beyond that, the wind turbine power output increases until it reaches the rated speed. And with this rated speed, output will be constant. But if it goes more than that, that is cut-off speed. When it is shut down, again, the power output will come to 0. Any questions so far?
Excuse me, sir. In slide number 30, so how we got the expression D equal to 1.52 square root of P?
This one?
Yes, sir.
So for that one, we just use like the typical values, like CP like 0.4, and then the rated speed we use 13 meter per second, and that rho value is given 1.25, and that A is given like this relation. And you can see here everything is known except P and D. And if you just simplify that one using those standard value, it will give you that relation.
Okay, got it, sir. Thank you.
Thank you. Now, so far, I just talk about wind turbine, but as I say, like the wind generation system. It's not only turbine, it has got other component as well. And here you can see that this is the input wind, which is coming as a input to the wind turbine rotor. And here you have got kinetic energy, which is captured by that turbine and converted to the rotational mechanical energy. And this mechanical energy, this is also connected with the generator through a gearbox. And the reason we are using gearbox because the speed of the wind turbine and speed of the generator are not the same. In most of the cases, the speed of the generator are much higher than the wind turbine. So that's why, like a transformer, that for the transformer input and output, we have got different voltage magnitude. It's for like stepping up or stepping down. And here, this is the transformer, which is called like a speed transformation. So it's quite equivalent to transformer. And then it connected with a generator. And as you know that it's a very simple. When you have got a input mechanical energy with generator, we can convert that into electrical energy. And here, in most of the cases, we normally use a synchronous machine like induction generator, but sometimes we also use like permanent magnet synchronous generator as well. And then we have got power converter just to control active reactive power as well as the frequency, because in most of the cases here you will get the variable frequency, but for the grid you know that we need fixed 50 hertz. And also like the voltage that we are getting from here, that is not suitable for connecting with the grid. So that's why we need in most of the cases, step up voltage for the grid. So here in most of the cases, like, you will be generating maybe, around 690, 700 volt, but that grid voltage are not the same. So we need a transformer, to step up that one. So the below, diagram exactly shows the same thing, but it just shows like, what the different input and output coming for the different devices. That's I already mentioned here. So if you would like to model, here, there are two important factors will come. One is wind speed and another is pitch angle, like for those blade, the angle that's, it has with the input wind. And sometime if you have got advanced like control, the pitch angle will change depending on the direction of the wind speed just to capture maximum power from the wind. And that is actually done by, pitch angle controller. So another terminology also, you need to know when, you'll be analyzing wind turbine performance, that is called tip speed ratio. And the tip speed ratio is defined by this equation where you have got tip speed of the blade and the wind speed. And the tip speed of the blade is given by omega r. R is the radius of the blade, and this is like angular velocity, omega, which is unit is radian per second, and v is the like in the wind velocity. There are, in terms of construction, there are mainly two types of wind turbine. One is horizontal axis wind turbine, and the second one is vertical axis wind turbine. And both have their own advantages as well as disadvantages. So when you have got like a small scale in residential area, if you would like to install, I think that vertical axis wind turbine would be the most suitable one. It has got lower ratings, but also you will get like, less noise and small space for installation. but for the normally for the commercial installation, we normally use horizontal axis wind turbine. So it has got higher capacity than the vertical axis wind turbine. So I already mentioned like that, for a small residential application, we use vertical. And if you compare like, vertical and horizontal axis, this one horizontal axis has got, higher efficiency than the vertical one. So this one also I already mentioned, there are mainly two types of electrical machine normally used in the wind turbine. One is asynchronous and another is synchronous. In asynchronous, also we have got squirrel case rotor type generator. So the other one also use one rotor induction generator. For synchronous case, mostly use permanent magnet, but there are also like excited one rotor excited synchronous generator as well. Next, I'll talk about different types of wind turbine technology. But before that, I'll give you like 5 minutes break. And this time, if you have got any question or comments, feel free to share with me. So if you have got any question or comments, feel free to share with me. Otherwise, I'll just take 5 minutes break. If you would like to have a cup of tea or go outside, feel free to do it. So far, still, we have focused on the basic of wind turbine. But I'll show you some of my, research output relevant to wind turbine as well. Although, I did it like probably 6-7 years back, because recently, I am not doing any work on wind turbine because I've given like more focus on electric vehicles and photovoltaic system. All the participants are very quiet today. Is that probably the topics either most of you are not interested, or Is it something?
Maybe, maybe Monday blues, I told you.
Yeah. Okay. I'll share the slide again. Okay, let's start again. So for the next like 1 hour, so initially I'll be talking about, different types of wind technology. What are the challenges for integrating wind turbines in the grid? And then I'll also show you, some of my research outcome which are relevant to wind generation. So the first wind technology that came in the market and also initially, installed and connected with the power grid in different countries, that was called constant speed wind turbine. So there are mainly 4 types, and they are like constant speed, limited, variable speed, and then variable speed with partial scale frequency converter, and variable speed with full scale frequency converter. And the one that you can see here, that is the first generation wind turbine technology, which is constant speed one. And this is the overall block diagram for that particular technology. So initially here you have got turbine, and then like gearbox, which is connected with a squirrel cage induction generator. So this is the generation technology which is utilized in constant speed wind turbine. It also have a compensating capacitor as well as a soft starter for that particular wind turbine. And the reason actually we use compensating capacitor, because the squirrel case type induction generator, as you know that, when it is started, initially it actually consumes some reactive current from the grid just for the magnetization purposes. And that's why, if this sort of wind turbine is connected with the power grid, it has got negative impact on the voltage and also the power factor. So that's why, there is a requirement from the power grid that if you like to install this type of wind turbine, which is not, popular in recent year, but it was, used in different country previously, and still, some of them would be still, running in different countries. So there is a requirement from the grid that you have to provide some compensating device so that it does not, have any negative impact on the voltage at the point of common coupling. So that's why it used like compensating capacitor, and in many cases it's not only compensating capacitor, but sometimes it also utilize FAX devices even to provide like better performance from this wind turbine. And the reason we use soft starter, that is also probably well known to any electrical engineer, that induction generator during the starting time, it actually get very higher current from the system. So this starting current is 5 to 7 times higher than the rated current. So that's why initially, this switch is off, So that's why this SOP register, which is nothing but a like a control register, is connected in series, with this turbine. That's why this resistor helps to control the starting current coming, from the grid. And then when it is reaches to standard rated speed, the switch close. That's how we actually bypass that resistor. So this resistor is only for the starting. So its main disadvantages that it has got negative impact on the voltage, and also, as you know, that's the squirrel case induction generator. I mean, the speed variation you can make it, that's very low. So that's why I say like almost like a constant speed. So you cannot control the speed that much. And also it needs additional device like compensating capacitor or flex devices. But the advantages is that if you compare with the other technology, its cost is significantly lower than the other technology because it does not use any power electronics inverter converter. And also the mechanical design of that squirrel case induction generator is very robust. So it needs actually less maintenance as well. So that's I already mentioned. Its advantages, disadvantages. Another problem that it also produces flickers and oscillation in the system as well, because you can't control the power like that. You can do it for the next generation wind turbine. So the second generation was it's a variable, but it's very limited. And instead of squirrel case induction generator, where you can see that here, like inside the rotor are short circuited, it's not connecting with any external devices. But here you can see that the rotor is connected. It's not short circuited internally. It's connected with a resistance box. Here, I mean, you can actually control that resistance. So by controlling that resistance, you can actually control the torque, and that's how, I mean, you have got limited control in the speed as well. But again, for this one also, I mean, we need a reactive compensator. So the only advantage compared to the previous one, that, I mean, you can control the speed with a limited range, but it has got this advantage as well, because here you are using resistance box which produces heat, and also like you will lose power in the resistance box as well. So the third generation one, and which is also the dominating one in the market and also popular in recent year, that is called a variable speed with partial scale frequency converter. And here the generator we use, we call it doubly fed induction generator. And the reason we call it doubly fed because both stator as well as rotor is connected with the grid. So the stator is directly connected to the grid through this inverter, but the rotor is connected with the grid through back-to-back converter. So you have got both rotor side converter as well as grid side converter. Both of them, I mean, you can control. So here almost 70% power goes to the grid directly through that stator, but the remaining 25 to 30% power goes to that grid through this power electronics converter. So here you cannot control 100% power, but at the same time you can partially control the power. So you have got at least 30% control capability. So that's why it's called like partial power electronic converter, because you are not controlling 100% power, which is coming from this generator. So that's why it actually provides better performance if you compare like the first two that I discussed in previous two slide. So it has got better power quality. You can control active reactive power. So that's how you can control the voltage using that grid size converter, and also the power and speed using the rotor side converter as well. But the disadvantage would be that it will be costly, because this power electronics converter are very, very expensive. And you know that here you need a very high capacity, like all the 30%. But even if you think about, for example, let's say 8 megawatt wind turbine, so the 30% of the 8 megawatt is still a huge capacity for a power electronic converter. And as you know, the power electronic converter is very sensitive. If there is a disturbance happening in the system, so if something happened, there is a possibility that your power electronic converter might be damaged. So that's why here you need a very intelligent protection and control system, so that even there is some disturbance in the system, your converter are protected and it does not damage that converter. So that's one I already mentioned, that it has got better speed as well as output power response, and you don't need like the additional capacitor that's we utilize in the previous two cases. And the fourth one, which is the next generation wind turbine, which might be popular in coming years. So here the difference with the previous one, that your 100% power you can control through this inverter converter. So here you will have better control capability, but the issue is that your inverter converter capacity would be equal or higher than the capacity of the wind turbine. And here also in most of the cases we use like permanent magnet generator or multiple generator as well. So this one will give you best performance, but in terms of the cost, the cost will be highest as well. So that's like the four wind turbine technology. Is there any question regarding wind turbine technology? Okay, if not, then I'll continue. So here, as I say, like that, you have got power electronic converter, which mainly does that, control for voltage, frequency, as well as power flow. And most of that control mainly achieved through this inverter converter. Only other than inverter converter, you have only control in the pitch control, which is like the in the mechanical side, but in the generation side, all the control that you can achieve through inverter converter. There are also like multiple different types of topology for inverter converter control are already available in the literature. So I'm just showing like one of them where you have got multi-winding generator. So here you can see that you could have like two level of VSC, and using that actually you can connect your multi-winding generator with the grid using this sort of converter technology. So as I mentioned, like for the turbine side, the maximum efficiency is 59%, but that is like more like a theoretical efficiency. So in most of the cases, like the efficiency might get 35% to 45%. So the another terminology also, I mean, you need to be familiarized. That is called capacity factor. So the capacity factor again, I mean, is the ratio of the total capacity of a wind farm with that, what actually you are getting as an output. So in most of the cases, the capacity factor is 20 to 140%. So for example, if you have a wind farm where you have got number of wind turbines, and let's say the overall capacity of the wind farm is 100 megawatt. So for a 100 megawatt capacity wind farm, you can expect that you might get maximum like 40 megawatt for wind turbine output at any instance of time. So that's how probably you have to plan. When you are designing the system in the wind turbine. So it's in most of the cases, the capacity factor is 20% to 40%. So that's, I already mentioned that the biggest challenge is that its output power is variable and it's also intermittent. So, you can't control it. It depends on wind power, and power output also changes significantly, like, from hour, daily, seasonally. So even if you think like a 24 hours, you won't get same output for like every hours. Even if you do like a weekly for like 7 days, you will get different outputs from a either single or wind turbine or a wind farm, and same for like seasonally. If you compare like summer, winter, your output power also will be different. So if you plan to design any system like the one that we discussed last time for a photovoltaic system, even for wind turbine also, you need to consider like that power you're coming in different time scale. So that's why is always recommended to have a mix of generation. That's might help to improve the capacity factor. Still, as you know that many community they don't like wind turbine, but one of the main reason they say that wind turbine are very noisy. But the good news is that in recent years, there have been many new technology where you have got very low level of noise. Even the latest one, it has been found that the noise level even less than half of the noise that is being produced by a swimming pool pump motor. So what I'm trying to say that in recent year, noise is not an issue in most of the cases. If you would like to install the wind turbine. How efficient? So again, if you compare with the efficiency, like in most of the cases, even it would be comparable to the current generating device that we utilize. So here I have just given like one comparison with the coal, like for coal-fired power station. Loss about 2/3 of the total energy is burned. So the losses is like 35% of energy. And then for transmission and distribution, you have got like 11 to 15% losses. So even if you consider, let's say like 13% in middle, then your overall efficiency would be that this 33%, and then here you have got another 13% losses. That means efficiency is 87%. So if you multiply that, your efficiency would be like like less than 30%. And even for wind turbine, like, let's say like efficiency, overall efficiency is like 30%, and here the losses would be lower in the line because it's very close to the load center. And let's say like 1 to 2% efficiency, that would give like comparable overall efficiency for wind turbine system as well. So this is not less efficient if you compare with the coal-fired power station. Grid integration, there are, as I said, there are many challenges. And one of them is just to have same control capability that we receive from a synchronous generator, because most of this coal, gas, or hydro, they utilize synchronous generator, which has got very excellent active and reactive power control capability. It also has got higher inertia if you compare with the wind turbine. So there is a challenge that, when you have got like large scale wind turbine in the system, it has got effect on stability as well as the frequency response, because as you know that it does not have the same inertia, which is very important. To manage the system stability when there is a change in the load demand or there are some disturbance in the system. And also like it does not have voltage and active power control capability like a synchronous generator. That's why in the system we often also get the stability issue in the system as well. So that's why probably we need better control for the inverter converter. That's why there are so many new research work are going on just to improve the converter capacity in order to achieve the same performance that we are getting from the synchronous generator based generating system. So the other new technology and also the popular that is being constructed in different countries, that's called offshore wind turbine. You might heard about that, because as community there always complain about the wind turbine, so it's a good idea to have like a offshore wind turbine. Also many countries they might not have enough space, so you can use those area that's are being like a water in the water, and you can generate that electricity, and then you can build a transmission line and transmit it. Although for offshore wind turbine, there are some challenges, but it has got many advantages as well. So some advantages that in most of the cases, if you compare like with onshore, in offshore we have got higher wind speed, so that's how you will get higher energy output from the turbine. So here it's just like an example that as I mentioned, like 15 megawatt 15 mile per hour wind speed will give you like a twice energy that will get like 12 meter per hour wind speed. So even like a small difference can make a huge difference in the output power. And also in the offshore you have got more steady wind speed if you compare with the onshore cases. And also like as I said, like if you have got limited land, the offshore will also give you that advantages. So you don't have to use like the land that you are utilizing for other purposes, and it does not consume any water either. Disadvantages, as you know, that's for initial construction, offshore wind farm might be more expensive and difficult to build and maintain if there are some fault happening in the system. The maintenance and repair cost will be higher. Still, its effect on the marine animals and birds are not fully understood. And also in most of the cases, we build offshore wind farm within few kilometers or few miles of the coastal line, which might not be liked by residents who live in the water side, and also that might not be liked by the tourism sector as well. So it might have some impact on the properties values, housing price. And in terms of the mechanical side also, as I said, there are some challenges. As I said, significantly high support structural cost, high operating maintenance cost, high electrical infrastructure cost, high wind turbine cost, and also strict standard for environmental as well. So in summary, these are the control objective you have got for a wind turbine. One is just like that, piece control in the mechanical side. Then you have got power regulation, active and reactive power. You also have speed control inside the mechanical. And also you might have load mitigation control just for the safety side in the wind turbine as well. And this one just shows like different controls that's happened. That's I already mentioned, like the generator and the piece control. And the piece control is mainly in the angle of the blade. And that can be done in many different ways. One of the way that would be that, you have, some sensor which will sense the speed and also see like the power that is coming. And if it is get like, low power, then it will see whether by changing the pitch angle, whether you can get more power, or even other control objective that when a very wind gust, it will sense, and that's how it will try to shut down the turbine as well. The converter control, as I mentioned, that it has got generator side and grid side, which has got different function. So here, as I say, like mainly for like the voltage and reactive power control, but for the generator side is mainly the speed control and active power control, and the piece control also that depends on the angle of the piece, which is also related to the power as well. Technical challenges I already mentioned, like I'll just skip that slide. Then I'll show you few research result that we have done in our research group. So the first thing we actually analyze dynamic voltage instability with different wind generation level and fast devices. And this is one of the project I was involved with some researcher from France, Germany. So we work with them just to analyze different scenario in 3 different countries. Then I also analyze what are the impact wind generator have on the transfer capability of the transmission line. Like we know that the power is transferred to the transmission line. So what impact wind generator can have on the transmission line capability. And then we also propose some control algorithm that can improve the performance of the wind generation system. So these are the cases initially we analyze just to see its impact on the dynamic voltage instability. So as I say, we consider several scenarios, but here I'm not mentioning all of them. So here, for example, one of them, we analyze that when you are importing like remote generation with a very high penetration. For example, let's say you have got like an offshore wind turbine, which is quite remote with a very high capacity, then what impact it can have on the voltage with and without FAX devices. We also compare, performance of different compensating device, for example, both with series as well as shunt compensation devices. We also analyze whether is there any like control interaction among different FAX devices. So when you have got like a number of FAX devices which are located close to each other, is there like a negative control interaction which might negatively impact the performance of the overall system? We also analyze the impact of two different technology. One is like a fixed speed wind generation with FAX devices, and another one with a doubly fed induction generator. And then we actually compared with the synchronous generator, because as I mentioned that our target to achieve the same performance that we get it from synchronous generator dominated system. And this is that system that we use initially for our Newark and New England system from USA, 69 bus system, and that is like a open source system. So the data are available online as well. So if anyone would like to utilize this system, the data is already available online. So here I'm just showing one result which is actually called the PV curve. PV curve is nothing but just one of the technique that we use to analyze voltage stability. So this is nothing but the relation between real power and reactive power. Now, here the cases that I'm showing here, what is shown here that when you have got coming very high power from remote places, and to that actually what we are using very high compensation device as well. So when you have very high compensation device, it will help to keep your voltage constant. But the problem is that if it is operating very close to that critical point, let's say if you have a system which is operating voltage is here, so or like here, so you are not experiencing any changes, like voltage is almost constant, but a slight shift will have a voltage collapse. But if you have a normal system, this power will slightly change with reactive power. It is not change suddenly. And this have been actually confirmed with a dynamic simulation as well. Just applying some disturbance, we found that when that operating point shifts, the voltage does not come back to the previous operating point. So there is a large possibility that although you are getting like constant voltage, but the possibility that if something happens, your system can be unstable. And then here with that same sort of capacity of fixed speed wind turbine, and then with the conventional generator, we compare the voltage response applying similar disturbance. So here you can that when you have got classical local generation, the power voltage coming back to the return point, but here your voltage is going down, so it is not coming back to the previous point. So the system voltage is getting unstable. So I'm not showing all the result because that's already been published, and if anyone is interested, I mean, all the analysis and findings that we have come up with different scenarios that's already available. Here, I mean, just some findings that I have highlighted here, that the system power transfer capability can be impacted by having like different wind turbine integration level, and also like in general cases, in most of the cases for the transmission line, the limiting factor is thermal limit. So that means through a transmission line, the maximum power you can transmit it, that is being limited by thermal limit. But when you have got large wind turbine, integration, that even might be limited by, voltage limit or stability limit, which comes before the thermal limit. So that means your system capacity have gone down due to that, high wind penetration. So we need, still we need better control, better optimization. I mean, to achieve same performance that we are getting from synchronous generator dominated system. So any question or comments so far? Any question or comments?
I don't think actually, maybe people are not working on wind.
Okay, anyway, then I'll just quickly go through the next few slides. So this is like one of the system that we use to determine the transfer capability. So here, let's say your area 1 could be like, one state, for example, like Delhi, and this could be another nearby state. I'm not sure what could be the nearby state, but let's say these two states are connected through this long, transmission line. And in most of the cases, like we don't have single interconnection. In most of the cases, we have got multiple interconnection, because if something happened, this long interconnection is still, you can transfer power, using the remaining interconnector. Now here, what we utilize that if you have got like normal generation, what the maximum power you can transfer, and then when you have got major power coming from wind sources, what's the maximum power you can transfer without using any compensating devices in those two nearby buses. So here it's just showing like the available transfer capability that we have achieved with different wind integration level. And as you can see, because that system is actually quite high. So even if you go to 10% fixed speed wind generator, which does not have any control capability, you can see that transfer capability actually have gone down significantly. So that's why, if you want to reduce that trend, we need that, better compensator device. And one of the best compensating device is called static synchronous compensator, which is also called STATCOM. So if you connect that one with a fixed speed wind turbine, it will actually help to improve that overall system performance. And to do that with fixed speed wind turbine as well as STATCOM, we have actually implemented different control. So, and the reason because we use STATCOM, as I mentioned, it provides very fast reactive power control devices, And although, as I say, like, doubly-fed induction generator are popular one, but still there are 30% install capacity of from squirrel cage induction generator. And this one does not have like, low voltage right through capability. And that is also one of the requirement currently if you want to install wind turbine. So if you want to provide that low voltage right through capability for squirrel cage induction generator, you can utilize STATCOM with this induction generator. That might give you that, capability so that you can integrate with the grid. And here, actually, we presented 4 different control for that combination of fixed speed wind turbine as well as STATCOM. And as we would like to make it robust, we considered uncertainty in our modeling and control design. And the way that we model uncertainty, one is called structure, another is unstructured. Then we also use simultaneous STATCOM as well as pitch angle control, not only STATCOM, but also at the same time controlling the pitch angle as well. And in other cases, we also consider STATCOM with a energy storage device. Because if you have got STATCOM, you can only control reactive power, that means voltage. But if you have got a energy storage devices, you can control both active and reactive power. And that's how its operation would be quite similar like a doubly-fed induction generator. And this is the low voltage right through requirement that, let's say, initially your voltage is 1 per unit, and suddenly due to a disturbance, it has got 0, it remains 0, like up to 0.525, second. And then the requirement is that next like 0.5 second, your power should come up, at least 0.95 per unit. So if you can meet that demand, that means you have got that low voltage right through capability. If you don't have it, when it goes 0 voltage, it's shut down the system, and that is not allowed by power grid. So again, I'm not sure. I know whether you will understand, but this is the control diagram that we utilize, for that STATCOM with energy storage system. So here, this is the STATCOM. So STATCOM is nothing but some combination with capacitor inductor with power electronics control, which have got like a voltage source inverter. And as I said, like with the DC side, you have got a energy storage which is connected to the DC to DC converter. So here we have got that controller which is measuring the voltage coming from the STATCOM terminal, and also this DC bus voltage which is coming from the DC side. And using that one also you can control that rate of charging for the energy storage devices. And also you can maintain the constant DC voltage at the bus here as well. So that's why we model the system. So initially we tried like a decentralized controller. Then also we did centralized as well as distributed. So the decentralized one, we only consider local input and output signal. So here we have got number of devices. So if you have got like 5 wind turbine, you are using like like a 5 control. So here we just mentioned like n number of wind turbines. So it could be any numbers. So here, as I said, like you have got local measured output, local control input. We are not measuring anything outside, and we are not using any communication. But if you would like to use centralized, you need the communication. If you use distributed, you need minimum communication. So in our case, our contribution was like that. We use some, local uncertainty that we generally neglect when we design control. And we also use that interaction between to neighboring devices, and that's how it actually contribute to get better performance for the control that we proposed. And this is the mathematical representation for the whole system that we utilize. So this is again nothing but that linearized part. This is the the local uncertainty, and this is the interconnection uncertainty. And then we define what are the signal that we are measuring, what are the term that might uncertain. We exactly don't know. After defining all those parameters, we determine all the matrices that you can see it here. And then this is just like the step-by-step method for the control that we developed. So the way that we design the control, so the first one from simulation, we actually come up with the group of generating unit. We call it coherent group, because what can happen like that in your system, we can have like hundreds and hundreds of generators, right? And if you want to model the individual generators separately, your modeling complexity will grow and grow. So that's why, I mean, if you can classify, similar group of generator which have got same behavior, you can represent those generated by simple, same model. So that's why you can have, lower order system. So we did that, and then we did some other small signal instability analysis just to find out which is actually making the system unstable and what signal we should utilize as a feedback signal to make the system stable. And then from different setup simulation, we come up that what are the area that we need to cover if we want to maintain the low voltage right through capability. And that's how we design the control, and then we tested the control performance using this 10 machine 39 bus New England system. That is also like a benchmark system for IEEE. If you would like to do study in the transmission side, and then we just compare the performance with a PI control with our control by applying some disturbance in the system. And here you can see that with our control, even like the voltage goes very low due to like a short circuit fault, but again after few seconds the system voltage goes back to the unity and it provides like a stable performance. And here we have to analyze that if you don't use energy storage device, you might see some oscillation in the real power output. But if you have a StartCom with ESS, it will give you very stable, energy output for the overall system. Okay. That's all for today. So again, if you have got any question or comment, feel free to share with me. But I'm sorry that probably many of you are not working with the wind turbine. But I believe that at least you have got some basic idea now what you can do with the wind turbine, how you can model it, how you can find the performance parameter, and what sort of challenges wind turbine have when you would like to integrate, and not all the challenges have already been addressed. Still there are many challenges are remaining. So if you would like to do research mainly for offshore wind turbine, there are still many issue, and one of them is like a subsynchronous oscillation. That is like one of the issue currently many people are working on. Yeah, so tomorrow presentation would be less technical. We will be talking about green hydrogen. So I'll also invite one of my students who have recently started working on for the planning and having interaction between power sector and hydrogen. And hopefully all of you will enjoy tomorrow's presentation.
Thank you, Jahangir.
So any question or comments?
Sir,
Yeah.
sir, is there any effect of wake dynamics on the power generated by a turbine? Because the dynamics usually occur after the wind has passed the blade, but I was wondering if it would have any effect on the ultimate power that is being generated by the thing itself.
I mean, as you have shown that, like, when you are thinking like the overall, generation that you are getting from the whole system, which is the combination of your blade, that means your turbine, then you have got your shaft, and then you have got your wind, electrical generator, inverter, converter. So if you have any effect in any part of this system, finally it will have that impact in terms of like the overall output power. But in terms of the grid impact, if you have got a very reliable and intelligent control for your inverter converter, so some of the issue that might happen in the turbine, that could be mitigated through your inverter converter control system. But in terms of the amount of the output power that we will be getting, definitely it will have impact on the magnitude of the output power. But the quality of the power might be mitigated by using better control in the inverter converter system.
Okay. Okay, so then voltage stability is being given an extra level of importance when a wind farm is integrated to a grid. If so, why is that, sir?
Because as I said, like, for any grid, there is a grid constant. If you cannot satisfy, you won't be able to, integrate, your device in the system. And it gives like more importance on the voltage because, as I say, like, it does not have the same voltage control capability like the synchronous generator. And also, like, as I say, like, some of the technology, even instead of supplying reactive power to the system, it actually consume or suck reactive power from the system. And when you are sucking reactive power from the system, that means you are
Voltage
having
dips down.
a negative impact on the voltage.
Yeah.
So that's why you need either some compensation device or better inverter converter that can control not only active power but also the reactive power, which is related to the voltage stability.
Okay. Okay, sir.
Sir,
Yes.
sir, in one of the slides you have shown uncertainty for n number of generators,
Yeah.
n number of plants. So what type of uncertainties are we, how to model that
here-
uncertainty?
So the uncertainty that we considered, one of them is that the parameter value. So even if you have a data sheet for synchronous generator, inverter, converter, but that data sheet give you the value for resistor or inductor for the ideal condition that they have measured those value. But when you are integrating that one in the real system, where you don't have that same operating condition, for example, that temperature, right? And also, while you are using the wind turbine, I mean, when the time progress, I mean, you won't expect that you are getting same performance and the same parameter. So there is some uncertainty in the all the parameters that we utilize. And also, I mean, when we model like wind turbine and that equation, I mean, mathematical equation we use, actually still, I mean, we don't capture like 100% true characteristics of the turbine. So in that case also, like in the non-linearity also, we have got some uncertainty. So these are some of them. And also, like, you know, you have got uncertainty in the, like, you know, in the, I mean, power output that you are getting from the turbine as well. So there are, like, you know, I mean, different types of uncertainty are associated with this. But for our case, we mainly consider the parameter uncertainty and the uncertainty that relevant to the non-linearity of the system.
Thank you, sir.
Thank you.
Thank you, Dr. Jangir.
Any system that you would like to use, I mean, if you want to make the system like, you know, robust, always, I mean, there are some uncertainty associated with that particular system, because for any system we don't know everything which is 100% correct.
Thank you.
Okay, Altaf, if there is no other question, I mean, we'll leave it here.
No, thank you for your lecture. Actually, I had a question. Is there
Yes.
any research which has been done on the compensators, the capacitor which is connected there?
The capacitor, you know, that is not a very new technology. I mean, this is
No,
like a
can you use something else there, or the sizing of the capacitor, something like that?
yes. I mean, definitely. I mean, for the sizing, there are some standard rule, but also, like, you know, there are some researches. But as I say, like, people are doing more research now on the StatCom, which is a replacement of the StatCom. So it has got much better I mean, performance, but it is slightly bit expensive. So if someone wants to do research on the compensating device, so instead of capacitor, I'll suggest to look for StatCom.
Yeah, and one request from my side for tomorrow, since you will be teaching green hydrogen, can we have 1 or 2 slides based on the context of the Indian subcontinent? How it will basically impact Indian energy consumption, or how is
Okay,
it
I mean,
like?
I'll try to find some information.
Yeah.
I mean, from Australian context, I know.
Yes.
But from Indian context, yeah. Thank you. Thanks for the suggestion.
Yeah. Thank you. So we'll
Thank you.
close for the day then.
Yeah, then. Okay.
Yeah.
Thanks, everyone.
Thank
Bye.
you very much, sir.
Yes, sir.